Okay, so this is the wrap-up video for the fan cart lab for Newton's second law. Okay, so the first graph that you came up with should have looked like this. Oh, I forgot to say put it in kilograms. I'll have to add that. Okay, and then meters per second squared. All right, and when you graph it, you should see something kind of that looks like this. Okay, and this is an inverse shape. All right, and we would say for the verbal model, right? No, not for every. Oops. Okay, as the mass increases, the acceleration decreases. Okay, and if you want to be really fancy, we should say under the same force. Okay, because remember we kept that constant the whole time. Okay, that's kind of important. All right, as the mass increases, the acceleration decreases under the same force. All right, so when you write this, you should have put like y1 squiggle k over x1, something like this in Desmos. Okay, which would give you an inverse equation that looks like this. All right. Okay, if I want to plug in the values that I have the acceleration equals, okay, then you're going to have some value here. You know, let's just say it's like 8 or something. I don't know what it was. Okay, over the mass. Okay, and you can write the words out if you want or whatever. All right, and I want you to think about what these units are going to be. Okay, so if I know this side has to come out to be meters per second squared, okay, and that's over a kilogram, all right, if I go to see what these units are, I get a kilogram meters per second squared, which hopefully you recognize as a Newton. Okay, so this should be 8 newtons. Okay, so your equation should look something like this. Okay, all right, this value I want you to think about, what does that tell me? Okay, that's a constant in the equation, right? It's that constant of proportionality in that equation, which means it's constant, right? That's why it's called the constant of the graph. What is this? Okay, and then go back to your original data and see if you can figure out what that is going to be. Okay, all right, let me see if there was anything else on that page that I missed. Inverse, equation of line. Oh, I should say shape. Constant. Okay, all right, general physics equation. All right, so basically, hopefully this is still on the first class kick page for this. All right, this one, since it's in newtons, you should recognize it as some kind of a force. Okay, so we can just say this for now, all right, but actually we're going to need to talk about what this force means. There was only one force acting on this because we didn't have friction. So this is actually what we call the net force. Okay, the net force means the same thing as the sum of the forces. It's like if I add them all together, like we have been, it's usually equal to 0, okay? But now, right, if I kind of multiply that, I can get this new equation, F net equals MA, or we'll say the sum of the forces equals MA, right? So before, right, remember we had this was always equal 0, and I told you don't just, you know, do that right, because that's not 0. Well, it's not 0 anymore. So everything about the problem-solving process is going to stay the same, but now instead of equaling 0, it's going to equal something else. Okay? All right, now on to the next slide if we want to linearize this. Okay? So if I have mass in kilograms versus A in meters per second squared, and it looks like this. Okay? If I want to manipulate one of these variables so that it comes out to be a line, right? Because I'm looking for this to be linearized. Okay? If my equation is F times basically 1 over M, or F over M, okay, you can see this is my new Y equals MX plus B. That's my new X. Okay, so if you manipulate all of your masses to be the inverse of mass and graph it, you should get a straight line. Okay, all right. Okay, so if we get that, then we have a y equals mx plus b. So we have an a equals, okay, whatever the slope is, okay, 8, times the x variable is now 1 over mass, okay, and hopefully this is 0. It should be pretty close to 0, okay, hopefully. All right, so again, we can see this is still the same equation as we had before, right? Because when you manipulate the variables and straighten the graph, it doesn't change the relationship. You're just looking at it through a different lens, okay? It's the same relationship, all right? Which if we want to switch it around again, we can just move the mass to the other side, and we still get the same thing, all right? So the slope now, right, would be 8 technically meters per second squared over 1 over kilogram, right? Because that's going to be the slope, the y units over the x units, which if I move that to the top, I can see again that's still a Newton. Okay. All right, and then the y-intercept would be 0, 1 over kilograms, 0 meters per second squared. All right. So if I have 0 inverse of masses, right? Okay, so, or if the inverse of mass is 0, what is the mass? Mathy folk. Okay, so if 1 over something is 0, that mass is going to be infinite. Okay, so when the mass is infinite, right, or 1 over mass is 0, means the same thing, the acceleration is 0. Okay, so it's really kind of a limit, right? Because we can see it's not really ever going to reach 1 over mass, right? We can't really have an infinite mass, but when we think about it, right, we can think about if the mass was infinitely big, right? If I applied a force to it, it would not accelerate, okay? But, you know, sort of a limit case, all right? I think that's that. Okay, great. So make sure you understand these graphs, okay? And make sure you understand the units of the graphs and how to straighten the graph, all right? And then on the next page, there'll be a little wrap-up of how to work the problems, okay? All right, but this equation here, I probably should have said this. I never like to say this. This is what we call Newton's second law, okay? Net force equals ma. Probably one of the most, if not the most famous equation in all of physics, okay? All right, yeah, that's it.